Unit 6. It's got to do with error, accuracy, and uncertainty. It's got to do with when we take measurements. You must realize, and I've said this to you already, when we measure something, what is the limit of accuracy on that instrument you are using? The smallest scale division. If it's a ruler, that's the amount of inaccuracy on it. Okay, now, the types of errors that we get when we take readings. Now remember, for you to use a ruler is fairly simple. But to use it correctly, you must know things like, be careful of the error of parallax. When you take a reading, your eye must be directly above the measurement. You can't look at it at an angle. Do you follow me? Okay, because all of these things cause errors. Okay, so, an absolute error is the one that is determined by the limitation instrument in the first place. In other words, your ruler is calibrated in millimeter, so you can't go more accurate than a millimeter. And then the next part, and the method of measuring. If you use that ruler incorrectly, you're not going to have a proper answer. All right. So an absolute error is determined by the limitation in the first place, and in the second place, how you the ruler is calibrated in millimeter. Remember that there is always an error. Millimeter reading you got actually implies it lies between two ends of plus and minus half a millimeter. Okay. There's therefore a range of possible values. Now, the next type of error is a relative error. Now, we express this error as a ratio or percentage, relative ratio or percentage. And very simply, if you take your ruler and you measure the width of your book, you can tell me, let's say it is 250 millimeters. If I say to you, take your rubber and measure the width of your rubber, you're quite large. You follow me? Because being out 1 millimeter on 15 millimeters is quite a large error. But being out 1 millimeter on 400 millimeters, it's so small, it's actually negligibly small. Do you understand? And that is what they mean by a relative error. An error of 1 centimeter on a measurement of 2 centimeters will be very significant. It's a 50% error. Okay? But an error of 1 centimeter on a measurement maybe of 10 meters, all right, is fairly insignificant. You follow me? All right. So, we say a relative error can be calculated as the absolute error. In other words, the reading that you've taken that is limited by the instrument and your method of using. All right? You take the absolute error and you divide it by a calculated value times 100 to convert to percentage. Systematic or determinate errors, a source of systematic errors, can be determined easily. You can find the source of the error, okay? Because it's easily notable, so it can easily be corrected. For example, if I have a spring balance, and I did not zero my scale on my spring balance, and I added a 10 Newton weight to it, my reading is 10.2 Newton. I add another 10 Newton, I will get 20.2 Newton. So I know where the error is. Oh, I didn't zero the scale. Okay, we can subtract it from our reading. Okay, so that would be a systematic or determinate error. We can determine where the error was, and we can correct it. Random or indeterminate errors are slightly more difficult to find because we don't know what we did wrong. Okay, and it can be, for example, a reading that is taken incorrectly. Okay, but if you take the reading incorrectly, consequently through your practical, you should also be able to get a result from it. But if you take a reading incorrectly now and your next reading you read correctly and the one after that is correct and the one after that is incorrect, it's going to be very difficult to get a decent set of readings. Okay, readings that are constantly done but not accurate. And I'll come back to precision and accuracy in a moment. Random errors can be eliminated by experience and by repeating the reading and taking an average. Remember when we said we need to make a test fair? To make the test fair, one of the things we must do is take an average. Because the more readings you try and take as good as possible, the more accurate your answer becomes. Okay, and it will eliminate maybe one error where you took one reading wrong. It cancels out that error. Okay. Let's get this here. And there. Let me just lock it in place. Okay, accuracy. The accuracy is limited by the scale division on the instrument. You can never be more accurate than the instrument. The higher the number of significant figures used, the more accurate, the higher the accuracy. Alright, so if I want to measure the diameter of a pipe for a precision engineering, if I need to make a fitting forward, I will use a specialized tool, not just a ruler. Okay, and we get specialized tools that have got a finer scale division to make it more accurate, and we will have a look at them in a while. Done. A ruler calibrated in centimeters will be less accurate than one calibrated in millimeters. I mean, that will also improve accuracy. Accurate values lie close to the true value. Here I've got a bullseye. If I am trying to hit the bullseye of the target, that's the true value. This one, there. All my shots hit the bullseye. It hit the true value. It's as close as possible to the true value as it can get. If I'm inaccurate over here because my readings are far away from the true value. If I have a fairly high accuracy, but some of my readings are around about, then I can say I have high accuracy, but I wasn't very precise. I made errors on some of my readings. Okay, and over here we have low accuracy, low precision. The accuracy, we were supposed to hit the bull. Only one of my shots hit the bull. So 1 out of, how many have I there? 7. I'm not very accurate. Was I precise in my error? No, it's all over the place. So I probably made different errors taking readings. So here we have precision is the ability to get the same result from experimental data. Okay. Yes. Probably. Okay. So the same result when values lie close to the true value, they are precise and close to the true value. When values are similar, but they lie far from the true value, there we go. Our accuracy is low, but our precision is high. And when values are spread out all over the show, we did not work accurately and we did not work precisely. Our answers are not accurate and they are not precise. Then we get something called an anomalous result. If you take a set of readings and you set it up in a table, and from the table you must go and draw a graph, and you find that as you plotted your points on the graph, there was one point that sort of didn't fit the pattern. Are you going to adjust your graph like that? No, never. Okay? You will draw a straight line through as many or as close to as many of the plotted points possible. Please use a ruler to draw a straight line. We will ignore the anomalous result. Here I have another graph. Or am I going to draw the graph as it is drawn here on the board? Nope. I draw the anomalous result and draw a straight line. Do you follow me? If you're busy with the experiment and you realize this reading does not fit the pattern, you can throw the reading out and redo that one. Okay. If you keep getting one that doesn't fit, then you ignore it and you carry on if you've got 10 others that do fit. Do you understand? All right. Anomalous results. And lastly, a little bit on uncertainty. Goodness me, there. Let's just lock it. Lock in place. Okay. Uncertainty, people, we said every measurement has a certain amount of uncertainty. This is determined by the unit in which it's calibrated. You can never be more accurate than the instrument. So a ruler calibrated in millimeters means that the closest reading that you can get would be to the nearest millimeter. It also means that on that nearest millimeter there is an error of 0.5 millimeter up and 0.5 millimeter down. Okay. If you have a bathroom scale at home, you will see on the scale somewhere, I think it's calibrated to be accurate to the nearest 100 grams. So if you get onto that scale and it says you have a mass of 55.6 kilograms, it is going to be, or 100 gram is going to be 55 point, let's say, 67 grams. So the accuracy at the 67, that's 7/100th of a gram, of a kilogram, is not accurate. You understand? There's 100 gram, so 50 gram up and 50 gram down from the reading on the bathroom scale. You follow me? Okay, so uncertainties in readings can come from the measure. It can come from the item or the object being measured. Sometimes it's very difficult to hold the object still. It doesn't want to stand still. It's a living thing that's bouncing around. Or you have to take the measurement in a very, very dark room and you don't have a good light on you to make the reading. Okay. Also, uncertainty can come from the person doing the reading. If I have to read millimeters without my glasses, I'm going to make an error. Okay. Uncertainties can be reduced by calibrating instruments correctly. Now, normally, when we buy a ruler, we don't worry much about the accuracy of the ruler because we usually use it to draw straight lines. But if I need to measure the diameter of a pipe, I'm going to buy a caliper or micrometer, which has a higher level of accuracy. Okay, so you need to choose the correct instrument as well. And then your data must be recorded accurately. Now that one sounds stupid, but when it starts getting tired and your concentration sort of lags, then very often, instead of writing down a reading of 3.25, we go and write down a reading of 5.23. Do you understand? Okay, it's just human error. And it usually happens when you start getting tired or working under pressure, that something is upsetting you and you can't concentrate. Okay, so working with results and drawing conclusions, we can compare results with one another, usually by drawing graphs. Okay, then possible ways of preventing errors: repeat and take an average. Know how to operate the apparatus. A millimeter ruler to a grade 1 learner and I say, okay, measure the width of the book in millimeters. Are they going to do it correctly? Probably not. They'll probably take the centimeter reading and give that they get. Do you understand? You need to know how to work with the apparatus. Avoid the error of parallax. That's a very common error that we make when taking volume readings, mass readings, balance readings, etc. Many of the newer instruments have got a digital display. And that, to a large extent, avoids, okay, because it's easier just to take the digital reading. accuracy and uncertainty. And once again, yes, due to the instrument, it limits us so that there is always an error on your reading. And the error would be to the closest unit, the smallest unit on your instrument. The finest division on your ruler has millimeters, so the accuracy is to the nearest millimeter. It means that even your reading, if it's given in millimeters, is going to be out by plus or minus half a millimeter up and half a millimeter down. Your answer lies somewhere in between. All right. A relative error, we said normally it's expressed as a ratio or a percentage. For example, the example we did this morning as well, an error of 1 centimeter on a 2 centimeter reading is major, it's a 50% error. But an error of 1 centimeter on 250 centimeters is almost nothing. Okay. Not significant then if we have 1 centimeter on 10 meters. Relative error is the absolute error divided by the calculated value times 100 over 1. No, it's just a relative error. You can give it as a percentage or just as a value. Systematic or determinate errors, we said source of a systematic error, we can find it easily and we can correct it easily. All right, it's something that you've done wrong consequently throughout your, maybe you took the reading on the edge of the calibration instead of in the middle, or, yeah, okay. Random or indeterminate errors, we said, are more difficult to pinpoint. We don't really know where they lie. Sometimes we've just taken a reading incorrectly. Sometimes you just didn't concentrate and you made an error, all right? Random or indeterminate errors. Accuracy. The accuracy of your instrument is limited by its divisions that it's calibrated in. All right? You can never be more accurate than the instrument. Because the calibration of the instrument, if it is in millimeters, you cannot be more accurate than that millimeter because that millimeter already has an error on it. So I can't say 15,275 millimeters. That's totally absurd. All right, it's a ridiculous answer because the millimeter 27 is already inaccurate. Okay. They say the higher the number of significant figures used to record a measurement and present calculated data, the higher the accuracy. But remember, it is limited by the instrument. You cannot be more accurate than the instrument. That's impossible. If I have my ruler calibrated not in millimeters, but in tenths of a millimeter. Okay. We can improve accuracy by repeating measurements and calculating an average. Usually in science we do a minimum of 3. The more repetitions, the more accurate it becomes. Accurate values lie very close to the true value. I'll come back to that term in a moment. Precision, to be precise. The ability to get the same result from experimental data. Then you are precise. When values lie close to the true value, they are precise and accurate. So does being precise and being accurate mean the same thing? No, it doesn't. All right. I'll show you here. I have a target, and I am shooting my bow and arrow into the target. All right? I want to hit the bullseye, dead center. We take how many shots? 1, 2, 3, 4, 5, 6 shots, and we see what they do. Can you see over here? All the shots landed all over the show. So I wasn't very accurate because I didn't hit the bull many times. And I wasn't very precise because my shots went all over the show. Yeah, exactly that. All right. Here, My accuracy wasn't good because I didn't hit the ball. Okay? But it was very precise because all my shots are concentrated here in one place. Right. Here we have high accuracy because they're almost all in the ball, but they're not grouped tightly together. So not very precise. And over here, high accuracy, high precision, high accuracy because I hit the ball, I was accurate, and all my readings are together, close together. All right. So they are precise. All right. Anomalous results. What's an anomalous result? One that doesn't fit the pattern. How do we treat anomalous results? We ignore them. All right. You can try and retake the reading. Sometimes it does solve that one. Sometimes it's not always possible to go back and retake the reading because you take your readings and then the next day you plot your graph. So maybe it's not possible to go back. All right. Is an anomalous result. And that one is an anomalous result. It does not fit the pattern. Ignore it. If I'm working out an average of these values, will I use that one? What do we do with anomalous results? You ignore it. You will use it to work out the average. No, it's anomalous. You ignore it. No, you ignore an anomalous result. Okay? Don't let it confuse you. If you've identified it as being an anomalous result, we know it's incorrect for whatever reason. So you don't want to make your readings inaccurate by using it. No. Okay. You understand? Uncertainty. Every measurement that we take has a certain amount of uncertainty. Once again, if we use our ruler calibrated in millimeters, the uncertainty is a millimeter, half a millimeter up, half a millimeter down, or front or back. So a ruler calibrated in millimeter will mean that the closest reading that you can get would be to the nearest millimeter. You cannot be more accurate than the instrument, and that millimeter reading implies there is an error of half a millimeter on both sides of it. Okay, half a millimeter more and half a millimeter less. So your answer should actually lie within a range. It's just not always when we write answers for measurements, it's not always if I said what's the width of your book to go and tell me 241 to 42 millimeters. Between those two is the width of the book. You understand? You will say 241, implying there is an error on the last unit. Okay. So, the uncertainties come first and foremost from the measuring instrument, then the object being measured, if it's standing still or if it's a very soft material with not a well-defined edge. There are certain factors that can make it difficult to measure things. And then the person doing the measurement, if he knows what he's doing, there should be smaller errors than if he doesn't know what he's doing. Okay? Uncertainties can be reduced by calibrating instruments correctly. For example, if I work with the balance in the chemistry lab and I want to measure a mass of a specific substance, I zero the balance before I put the substance on it. Accurate calculations. In other words, we work out averages with which we do our calculations, and we need to record the data accurately. Human error. No. When we work with the results and we draw a conclusion, we will always compare results with one another by drawing graphs, because it's the easiest. If I'm working with how fast, what is your speed when you start running during the first 2 seconds of a race, everybody accelerates. The green graph is Ryk, and the red graph is me. He accelerates much faster than what I do. Okay. We compare the two graphs with each other. This one has a steeper gradient than that one, which if we have, what is this, a speed time graph, then that would be his acceleration, the gradient. Okay. Possible ways of preventing errors. People, it's common sense. Why do I list them like this? One of these papers that you have to write exams on is a so-called alternative to practical. And they go and give you a practical all in words with pictures and everything, and then they go and ask you, what could you go and do to this practical to make it more accurate? So now you have to go and look which of these things would be able to fit onto that practical. Okay, what can we do? So it's just sort of, it's just general of common sense stuff. Okay, yeah. Repeat measurements and take the average. Know how to work the apparatus. It doesn't help you have to work with a burette and you can't take the reading on a burette. Or if you have to work with a thermometer and you don't know where to take the reading. For that matter, if you have to work with a measuring tape and you don't know how the reading works on a measuring tape. Because that is also a problem. Do you understand? Okay. Avoid the error of parallax. Record the values correctly. In other words, concentrate. But everybody gets tired somewhere. It's very easy to make a mistake like that, especially when you're doing a lot of them over a long period of time. Round off numbers correctly. And be careful when you convert units. For example, kilogram to gram, or meters to centimeters, or millimeters. Okay?